Good afternoon and welcome to today's training on electricity system planning. We're going to start in 1 minute. Good afternoon and welcome. I'm Danielle Sass-Burnett with the National Association of Regulatory Utility Commissioners, NARUC, with the Center for Partnerships and Innovation. And we are excited to continue hosting this very timely and relevant series of trainings for our members. For those who aren't aware, the Center for Partnerships and Innovation has numerous resources available on our website about emerging industry issues, including distribution system planning, bulk power system issues, grid data sharing, and many others, and we'll provide a link to that in the chat in just a moment. This is the fourth webinar in our electricity system planning training series. We've developed this training in conjunction with the New England Conference of Public Utility Commissioners, NECPUC, and thanks to Meredith Hatfield for her time helping to work on this together. All NARUC members have been invited to participate in addition to those from New England. And we're also very grateful to the U.S. Department of Energy and Lawrence Berkeley National Laboratory for being key partners in pulling this training series together, especially Lisa Schwartz, who you'll hear from in just a few minutes. Today's training is on delivering grid modernization value by design. Recordings for this session and past sessions are on the NARUC website. And the next session on July 16th will be on state regulatory approaches for distribution planning. As I said, we are recording and the presentations will be available soon. We will put that link in the chat as well. And finally, before I turn things over, just a flag that we will ask you to fill out an evaluation after you attend the session today, which will help us ensure that our work in these types of events is relevant and timely and helping to enable you to do your jobs and make as best as possible. There will also be a separate survey late next month to get your feedback on the entire training series. And there's going to be an announcement about some office hours that are available with our expert speakers later this afternoon. So I think with that, I'm going to turn things over to Meredith Hatfield from NECPUC. And thank you all again for joining us today.
Great. Thank you so much, Danielle. Hi, everyone. I'm Meredith Hatfield from NECPUC. Thanks so much for joining us today. And I want to thank Danielle and Jessica and the whole team from NARUC. We really appreciate all your efforts in putting this series together. And I want to really thank Lisa Schwartz from Lawrence Berkeley National Lab and all of her work in pulling this together and bringing in some pretty awesome experts from many of the other labs. So Lisa, I'll turn it over to you.
Thanks so much to NARUC and the New England Conference of Public Utility Commissioners for participating. I'm Lisa Schwartz with Berkeley Lab. Thanks for joining us. The U.S. Department of Energy's Grid Modernization Laboratory Consortium is supporting this training for New England Public Utility Commissions, and we've also opened it up to commissions throughout the country and the public. Thanks today, especially to our sister lab, Pacific Northwest National Laboratory. He'll be providing training today on grid architecture. We'll be putting some links in the chat box. First is a link to today's presentation. Second is a link to the full bios and registration information for the training. And I hope you'll join us next week when June 16th, 2 to 3 p.m. Eastern, I'll be presenting with Natalie Mims-Frick on state regulatory approaches for distribution planning. And like Danielle mentioned, we'll be sending probably next week a flyer to New England commissions about the office hours we're offering with all of the experts in this training series. So you can sign up, you and your colleagues, to talk to them about a specific issue you're having in your state that relates to the topic that they talked about. So it's a great opportunity to get free help and some resources going forward. So back to today's training, we're going to be covering delivering grid modernization, value by design. So it's all about grid architecture, a really important topic. First, we have Dr. Seemita Powell. She's a senior research engineer and leader of the system engineering team in Pacific Northwest Lab's distributed Systems Group. And services, she also provides services for the grid architecture team at the lab. Among her current projects is developing a practical introductory guide to grid architecture for the Smart Electric Power Alliance. It's going to be a really valuable resource. Also, Dr. Ron Melton, he's a senior technical advisor for Pacific Northwest Labs Electricity, Infrastructure, and Buildings Division. And previously, he served as the lead for the lab's Distributed Systems Group. He's a member of the core team for DOE's Grid Architecture Project, and he serves as the administrator of the GridWise Architecture Council. Also, he's co-chair of the Grid Architecture Working Group of the Smart Electric Power Alliance. So they've got great credentials here for covering our topic today. I'll be moderating Q&A following their presentation. Please enter your questions at any time in the Q&A box, and we'll get to it right after their presentation. So let's get started with our session on grid architecture with Seemita and Ron.
So thank you, Lisa. I'm going to start things off. This is Ron Melton. So could we have the next slide, please? So today we're going to give you a 60,000-foot flyover of grid architecture and discuss how it applies to grid planning. We've got some examples of structures that we commonly use in the grid architecture work, examples of how grid architecture concepts have been used, and then we've come up with some questions we think that you might be interested in asking as you go through your deliberations as a commission, and we have a few takeaways for you. Next slide, please. So we're going to get started off with that overview of grid architecture as applied to grid planning. Next slide, please. So this is our basic background slide for you on grid architecture. Grid architecture has its roots in several areas of system science and engineering. It's based on work in system engineering, in particular the architecture of systems, as you see here, theory of networks and control systems engineering, and it applies elements of those areas to the electric power system or the grid. That's our label for this work of grid architecture. What is an architecture? You know, we've all seen architectures in terms of things like buildings, but what is an architecture just in its roots? As shown on this slide, an architecture is an abstract depiction or representation. For our purposes, we're dealing with components. Actually, we deal with classes of components, and we treat them as black boxes. For example, we can talk about a storage component. As a black box, we're only concerned with what is externally visible or observable. What goes in, what comes out, what behaviors can we observe? These are the concerns we have about a component. We don't concern ourselves with the physical system inside the box, the technologies and so forth, what kind of battery it might be, whether it's a battery at all or something else. That's not of interest to us. It's these externally observable things as a black box. You're probably already aware that several years ago, the National Academy of Engineering declared the electric power system to be the most complex machine ever built. Well, grid architecture enables us to create high-level, in other words, abstract representations of the ultra-large scale complexity of the grid. This in turn enables us to reason about the grid's properties, its behaviors, and its performance. We work to answer questions such as, what overall structure will enable devices to be integrated with the grid and each other, as opposed to more detailed technical questions such as, how should we interface device A to device B? And we do have a tremendous amount of work on this topic, reports, white papers, reference architectures, and so forth at the website that you see listed on this slide, gridarchitecture.pnnl.gov. Next slide, please. Oh, back one. There we go. Structure is one of the key elements of architecture. What is connected to what, as we'll see in some of our representations, and what is the nature of the connections? As we see on this slide, in the practice of grid architecture, we consider several different structural elements or views. Going through them sort of around the circle here, you see electric infrastructure. This is one that most of you are already familiar with, with things like circuit topology. What are the loads? What are the generation? How are these things connected together electrically? Industry structure. This may be a new concept to you, and we'll show you some examples of industry structure diagrams. This looks at things like operations, planning, markets, and so forth. Regulatory structure. Yes, we can draw diagrams that show the relationships between the entities involved in the regulatory processes, federal, state, and other. Digital infrastructure. This is extremely important in the modernized grid with the communications that's required with networking and things like that. Then the control structure. This would include things like protection systems, control systems, synchronization, and another structure that we often look at now called convergent networks. So this looks at the convergence between things like the electric power system, fuel delivery systems, transportation systems, and even potentially social systems. One new element that you'll see here in the blue box underneath grid structures is the coordination framework. This represents the set of relationships, processes, and flows that tie the grid together and get the parts to operate as a cooperative whole. One element of planning is to consider changes in structure. Structure as it is today provides context and a starting point for then considering proposed change. But there's often a gap today, and that's lack of knowledge of grid architecture, concepts and structures for distribution system planning. This is a gap we're trying to close with training like this. Now, to reiterate, planning should incorporate some knowledge of grid architecture concepts and actual grid architectural structures as they exist and as they will exist. And we're going to start taking a look at some of the ways that we do that with the next slide. So, as we mentioned, grid architecture is a work in abstraction. One question that we often get is, what's the relationship between grid architecture and design? We see here 3 levels of abstraction that are often used in system engineering and in grid architecture. The highest level of abstraction is what we're labeling as conceptual. This is the level at which much of our grid architecture work is performed. You see in the example in the box on the lower left, an excerpt from one of our industry structure diagrams, and Seemita will talk more about this in a few minutes. At this level of abstraction, many different implementations are possible. They will be consistent with that architectural representation, and they may use different physical components, different physical approaches, and so forth. The next level of abstraction down is the logical functional level. This is a more detailed representation, but it is still not a representation of the physical implementation. This example in the box in the middle shows part of our design of controls for a concept that we've developed from the grid architecture work called embedded storage, in which storage is placed at every transmission distribution substation in a balancing area. This step, we've now specified a design at a functional logical level, but not the technology or the physical design of how it will be implemented. Now, I happen to have learned years ago that this is quite commonly used in the communications industry, where technology changes rapidly. The industry maintains their designs in a logical functional level of abstraction, and then maps and remaps them over and over again to the physical design as the underlying technology changes. The lowest level of abstraction is, in fact, then the physical design. And we see in this particular example in the lower right, a traditional one-line diagram sort of representation, in this case of a model feeder system, something we call the 9500 node system, which is being proposed as an IEEE model feeder. It shows us something about the physical structure, connectivity, and some of the information about the components. Our grid architecture work is largely at the conceptual or the logical functional levels of abstraction. We are working right now, for example, to execute a project on distribution transformation. We're applying the conceptual work from the earlier DOE Grid Modernization Lab Consortium reference architectures to a more logical functional representation that provides a starting point for the changes to accommodate decarbonization of the electric power system. So with that, next slide, and I'll turn it over to Seemita for a bit.
Yes. So grid architecture is a practical tool for planning and designing the grid modernization. It enables us to understand the current system along with its complexities, and build a shared vision of what needs to change. So if you look at the top right, there you will see there are two boxes showing two diagrams. If you look at the left box, you will see some typical applications in the distribution system. You will find different sensors and communications tied to them. For example, you might have AMI system with its own meter, communication network, and application. There might be also a separate SCADA system feeding the distribution management system. Now, when the scenario arises that one of the applications wants data from sensor of another application, right now, what we need to do is look at their interfaces and do a lengthy backend integration, which is very expensive. Often it is more costly than even the base system. On top of that, this kind of a siloed architecture leads to poor flexibility, long latency, and can result in rippling impacts if change is made in one small system. So now let's imagine that we do a structural transformation and we go to the system to the right. So we take the sensing and communication and make into a sensor network. So now we have all the applications decoupled from each other. What does this do? So any application that is authorized can access that sensor network and obtain all the necessary data. Each sensor has the flexibility to serve multiple applications at the same time. And this also eliminates any costly integrations that are needed to be done right now for adding more applications. So just one structural change simplifies a lot of the downstream issues and future-proofs the existing applications and lowers the cost of future applications. So this kind of a structural transformation can be done using grid architecture concepts. And on the lower right, you see another structural transformation where you see different entity classes are interacting in a different way in the left, but that can cause tier bypassing. So we can do structural transformation to eliminate that tier bypassing. So this provides a rigorous basis in the planning process of grid modernization effort, where we can make well-informed decisions and proactively analyze and mitigate any undesirable implications. So getting the structure right and the pieces is incredibly important so that all the pieces fit into place neatly and all the downstream decisions are simplified and investments are future-proofed. Next slide, please. So if you have heard Jeff Taft, our founding father of grid architecture, give an introductory talk on grid architecture, you may have heard him ask this question. When you build a house, what do you pick up first? A shovel or a pencil? What do you think? Well, of course, it is a pencil. You need to plan it first instead of jumping to the execution step with a shovel. Then he said something that I will always remember. Often people try to hang the windows first. Please don't be a hang the windows first person. So in the utility industry, we often see that there are various solutions being proposed. I have a terrific window frame, which will solve a lot of your grid problems. Let's hang this first. And they might even bombard the public utility commissions. But what we need to do first is sit down with a pencil, think about the current structure, think about all those walls and where the window can go and what changes are needed to be made. So I can't stress enough on how important it is to make the decisions in the right order. Plan out the system before starting to build. Next slide, please. Those of you who have attended Paul Martini's grid modernization planning session in this training series have heard about this grid architecture approach. So this is an early stage process, important for strategy and planning. It starts with the principles, which are the formal basis of how we are going to develop the architecture. Then the next most important step is to understand the objectives. What are the forces involved behind the changes? And what are the emerging trends that need to be looked into? What are the issues that need to be overcome? We need to define the external qualities of the grid as viewed by the user. The user might want a safe, secure, resilient, reliable grid. These are the capabilities that are needed to be offered by the grid. This answers what kind of internal properties the grid should have in order to manifest those qualities. And those properties help us determine ultimately the system requirements. So expressing the scale and scope of the challenge at our hand and determining the right set of system requirements requires this formalized and systematic approach that grid architecture offers. And these system requirements are used to determine the structure and components. So like I said, don't be the hang the windows first person. Resist the temptation to start with the technology choices and let them be black boxes like Ron mentioned. Of course, we need to make sure the black box is a feasible one and we can do that with the technologies at our disposal. Over to you, Ron.
Thanks. Next slide. So as it says on this slide, planning is inherently about the future and change. Here we have an example for you of the nature of change, moving from a distribution operations model, in other words, operating the wires, to a model in which distribution markets or related control and coordination functionality have been introduced to the distribution system for the purposes of facilitating large-scale deployment of DER in front of and behind the meter in distribution systems, or a model that's often referred to as a DSO model or distribution system operator. So notice that the diagram shows that it's possible to construct parallel structures between the wires operation and the DO and the control and coordination of DER operation, the DSO, and then to consider the interaction between the two. By the way, we aren't showing this to say this is what should happen. We're showing this to illustrate the usefulness of such a representation and considering such changes in planning. For example, distribution markets have several features shown there in the lower left part of the diagram. The most fundamental feature is clearing and settlements, a function required by any market. The other elements, such as capacity, day ahead, and real-time dispatch, may or may not fit the needs and can be considered and discussed as options. Another thing to note is the connections between the two sides tell us something about the nature of information exchanged between the DSO construct and the DO construct. Note that the particular diagram is a construct that is largely derived from bulk power systems market operations. In planning, one might construct other distribution market structures that are derived from the work in distribution system transactive energy and that may have a different set of operational elements. Then one can start to compare and contrast the implications of choosing one or the other. So this helps us manage the overall complexity and helps us do the planning that Seemita was talking about with, starting with the pencil and not coming up with the clever solution and not evaluating it in context. So back to you, Seemita. Next slide.
Yes, so we start with what Ron said at the end. We need tools to manage system complexity. So complexity of the electric grid is further growing due to new technical, business, and environmental goals for which the grid was not designed. And we achieve that complexity management and risk management by using grid architecture. It provides us with all the frameworks, methodologies, techniques, and tools that we need to do that. And since we start with an understanding of the structure and the behavior, so we can do good reasoning about those. We also start with the qualities, system qualities, like I mentioned in one of the previous slides, and also think about the system characteristics in a systematic manner during the process. Therefore, we can do a good prediction of those along the way. And grid architecture is also incredibly important in stakeholder engagement, from defining objectives to inferring requirements, functions, roles, and responsibilities. The context provided by stakeholders is indispensable, but it is incredibly challenging when stakeholders have different backgrounds and interests, and we are dealing with an ultra large scale complex system. So grid architecture facilitates that communication and helps in understanding and sharing a common vision. Grid architecture diagrams provide us visual maps showing the key actors in a system and their key interactions and their relationships. This helps in identifying gaps in theory, technology, organization, or even regulation, if any. And these are specifically important when envisioning changes to this ultra-large complex system. With that, let's look at some of the commonly used grid architecture structures. So next slide, please. And next one slide more. Okay, so let's start with industry structure diagrams, which are one of the key diagrams of interest in grid architecture. What are these? So industry structure diagrams of any regional grid is basically a model providing a visualization of the entities, their functions, as well as their interrelationships. They are key to obtaining a complete picture of how these entities cooperate and coordinate their activities to provide seamless services. And like I said, it helps in managing complexity. We identify the stakeholders, we determine the different entity classes involved, we determine their interactions as well as understand the complexities which are involved in those interactions, and therefore define the complexity in a visual manner, which makes it simple to understand and helps stakeholders understand the complete picture. It is a tool for grid modernization, which helps us in understanding the present grid and helps us in planning the future. So with that, let's go to the next slide. So when you think of any regional grid, we may think of some specific stakeholders, and we often miss many other stakeholders that are involved in the industry. This diagram here is not the complete industry structure diagram. It just shows the entity classes involved in the industry structure of ERCOT's regional grid. In the center, we obviously have ERCOT serving multiple functions: reliability coordinator, balancing authority, transmission operator, transmission service provider, and market operator. It also helps with retail operations. In the top, you will find the different types of generation entity classes. In the left, we have the different regulatory bodies. In the right, we have the various wholesale market participants. And towards the lower half, we have the other transmission operators, distribution providers, retail electric providers, aggregators, and customers. So there are a lot of stakeholders involved. And do we take time to think of all these entity classes that are involved in the regions of our interest? Should we take time to think about all the different interactions? Probably we should. And these grid architecture diagrams give us all the tools and all the materials we need to do that. Next slide, please. So in the previous slide, we just showed the boxes, which are basically the entity classes. However, we also want to show the relationships between these entity classes. And these are shown by lines connecting them. And these lines have cardinality, which is basically how many of the entity class members are involved in a relationship. And it is shown by symbols indicated in the box in the top left. Directionality is also indicated in these through the use of angle brackets in the text description. For today's short training, we are not learning about industry structure diagrams in great details. We won't be looking into these nitty-gritty details for the one diagram that we will be viewing. But I want to pull your attention to one important concept. That's the concept of layering. So these entity classes serve several functions, and these are shown by 7 layers, and each layer is indicated by a different color. So control and coordination, energy and services are very technical layers, which are shown by different colors. Control and coordination is shown by red, energy and services by green. We can look at the market interactions, which refers to the wholesale market. And we can also the retail construct, which is shown by sea green color, and we also have federal and state regulation layers. Now let's look at ERCOT's complete industry structure diagram. So let's go to the next slide. So before going to view all the layers at once, let's look at a couple of the layers individually. So here you are seeing the state regulation layer. And as we would understand, PUCT plays the central role, and it's overseeing and regulating various entity classes in this layer. And therefore, we see those lines coming out of PUCT and connecting with various other boxes or entity classes in that diagram. Now, on the next click, we will see the control and coordination layer, where we see how the different entity classes are interacting with each other. One change in the control and coordination layer has the potential to cause rippling impacts on other controls. We can also see that a lot of different entity classes are coordinating to provide a seamless operation. On the next click, we will see the complete industry structure diagram with all the layers turned on. And we are not focusing on industry structure diagrams with great detail today, but just one insight that I would like you to take away from this is real-time markets are strongly connected to grid control and coordination, and regulation also has a role in the reliability and control and coordination. So we get insights about this coordination framework from the industry structure. We can see the other industry structure diagrams of other regions to understand how the industry works in those regions as well. Next slide, please. So now grid operators in the US are required to develop plans to allow DERs to access their multi-million-dollar wholesale energy markets, which essentially means we need to reshape the system. So the key players in grid operation have been transmission system operators, transmission owners, and distribution operators. In the future, we need to think how we can include DER owners, DER operators, which includes aggregators and customers in a more effective way. So that means certain functions need to be allocated to these different entity classes while making sure there is no tier bypassing or conflicts. So grid architecture is a key tool where you can look at the as-built system and you can vision the future system and analyze the different implications that are potentially possible if changes are made. And we can make better and well-informed decisions using this tool. Next slide, please. So with the industry structure approach, we were focusing more on the present system. And another tool that we have at our disposal is this technique, the framework for mapping from components to qualities. So this helps us look at the future and plan for it. So we start with the system qualities, which are the desired characteristics of the system. User needs and public policies determine the system qualities. We might want the system to be safe or reliable or affordable. And these are basically things that the user of the system will comment on. These system qualities determine the system properties, as you see in the middle column. What properties should the system have? And this is from the perspective of the operator. And these are the characteristics that the system should have to manifest those qualities that we mentioned. And the leftmost column shows the architectural elements. These are the elements that make it possible to have those system properties. So we can systematically go from the system qualities to the system properties and determine the architectural elements that are of prime interest to us. There is an online tool that the grid architecture team had developed that can be used to create these kind of mappings. And this is a key tool that can be used to determine what kind of policy changes would be most effective. Next slide, please. And we looked at the present system. We are planning for the future system. Another thing which is very important to note is this platform concept. So you may have heard about layered structures, which is a powerful architectural concept. And it is even more important when there are at least 3 layers or more, because the middle layer can separate and isolate the upper layer from the lower layer. So this prevents certain kinds of changes in either the upper or lower layer from propagating to everything else. And a platform is a system architecture approach that organizes these system elements such that common functions are grouped together and accessed by higher layers via services. We have seen this in different domains, including computer, hardware, software, vehicles, and even the internet. And this is a powerful concept that can be even used for grid modernization. It will help in separating the functions from the users. It will help provide a set of services and capabilities. It will help the platform be more stable over time, where the applications may change, but we don't have to do a lot of lengthy backend integration to integrate those. And it will decouple the changes from the underlying infrastructure. So this is something we should keep in mind when thinking of the different solutions during the course of the grid modernization planning effort. Next slide, please. So now we will give some examples of how grid architecture has been applied. Next slide, please. So the Hawaii Public Utility Commission said that the grid architecture is a practical tool for obtaining insights at the system level across multiple relevant domains, and therefore the commission encouraged stakeholders to provide their views on grid architecture and use those concepts for the grid modernization effort, and think how those concepts can be integrated into the company's different solutions. We also know about New York's reforming the energy vision effort. So in that, grid architecture concepts were used to develop the industry and market structure diagrams of New York, and reviews were done of proposed changes to business models and metrics to make sure that there were no unintended consequences of those changes. Also in Ohio, the Power Forward initiative suggests the use of cyber physical platform, which is needed to support the markets in the region. And we also know how modern distribution grid report volume 1 has been using some of the grid architecture concepts, specifically the platform concept that we looked at right before this slide. So with that, I will go to the next slide. Next slide, please. So here we look at some of the concepts that have come up repeatedly during today's talk. So the Ohio Power Forward Roadmap calls out the platform approach, the platform concept, that it creates opportunity for entities to provide and innovate products and services to customers in a more planned fashion. It also calls out the networks that connects all the users of the platform. So those are some of the key grid architecture concepts that have been picked up by Ohio and are being used. So with that, I'll hand it over to Ron. Next slide, please.
Yeah, thank you, Seemita. So just to sort of let you know, the grid architecture work has really become an international effort. And in particular, our colleagues in Australia have been paying close attention to what we've been doing. This is an example of their application of the work and considering changes to their system. Stratagen, who did this work, is a consulting company in the US and Australia. And they've recently led the development of initial work on planning changes in the Australian Energy Market Operation, or for the Australian Energy Market Operator, AEMO, in response to their large-scale DER deployments in Australia. You see here a particular graphic that I happen to like that summarizes that change. It's similar to ones you may have seen before, depicting changes that come about due to decarbonizing the electric power system. To me, the largest contrast is on the right side of the diagram, where we see the shift from one-way flow of power with passive consumption on the top to multi-directional flow of power with actively engaged system elements in the bottom right. So high-level diagrams like this are really helpful in communicating the basic structural changes to a variety of stakeholders. They are often followed by more complex representations, such as the ones that Seemita showed you, in particular industry structure diagrams, or the diagram contrasting the DO and DSO models. Next slide, please. So Seemita mentioned platforms, and this is a diagram you may have already seen if you attended one of Paul DiMartini's presentations in the training series. And we thought it was worth revisiting today to further discuss platforms. They're a very important architectural approach that we apply in quite a bit of our grid architecture work. As Seemita mentioned, platforms are an example of a layered structure. We saw actually in that DSO-DO model a few minutes ago a platform structure, and you may have noticed the layering in that diagram. This slide takes elements of distribution system operations of today, and it organizes them into a platform representation. Unfortunately, the industry still primarily uses single vendor solutions that are often siloed and don't get the full advantage of platform structures. Some features of the diagram that relate to the platform features that Seemita covered are, first of all, separation of the foundational functionality from applications. So you see that in the labels on the right-hand side. Provision of services and capabilities that are useful to many applications. For example, note the top green layer of operational data management, making data widely available to the elements of the platform above it. And receiving data from the layer below it, sensing and measurement. We also typically get improved scalability with a platform approach. And as Seemita mentioned, decoupling of changes between the layers. This particular decoupling can be extremely important in enabling technology upgrades and avoiding stranded assets. It's also important in achieving interoperability with reasonable integration costs. Now let's take a look at a platform approach for where things are headed in the future. Next slide, please. So in this slide, we see another example specific to software for distribution management systems. Software and computing platforms are quite common. And if you have a smartphone, you're already familiar with two of the most common platforms, iOS for Apple and Android for Google. In the electric power industry, platform architectures are beginning to be used, for example, in ADMS and in some smart metering systems, for example, the Itron Riva platform. But they tend to be closed platforms with proprietary interfaces and data formats. On this slide, we have a conceptual design of an open architecture, open source software platform called GridAppsD, which is a DOE-funded project that we've developed to enable the industry to have portable applications. So I mentioned iOS and Android, and you're familiar with App Store. So think of the ability to have a distribution management app store. Now, as a national lab, we can't compete with industry. So we haven't developed this as a product, but we've developed this as an application development tool. And in this application development tool, we have an open architecture. And by that, I mean that the interface specifications are open and available, as well as the data formats and so forth. By taking advantage of existing standards, notably the Common Information Model for distribution system network representations, we're able to separate the problem of data integration from the problem of applications or functionality. We do this by providing a standardized interface between applications and data. Further, as intended within the concept of advanced distribution management systems, all data is integrated into a single data bus, enabling an application to use all available data from all available sources. So you see that in the purple bar right in the middle of the diagram. It says standards-based data bus. In our case, the distribution simulator underneath it is the source of data that goes into the data bus. In an implementation of a system along this approach, that would be where the SCADA system would plug in. And the red box in the middle above it is the place where the standardized interface between applications and the data is represented. You'll note also that this has considered the possibility of interacting with legacy systems off on the right-hand side. So we really think that this is an important approach, and we've been extending it to support distributed functionality. As we see more and more deployment of distributed energy resources in distribution systems and increasing variable energy resources throughout the system, as well as electrification of loads, in particular transportation, the complexity of the system is going to increase dramatically, where we believe that the future will be built on distributed functionality. And so we've been extending this work to support that and distributed architectures. With that, back to you, Seemita. Next slide, please.
Yes, so you might be thinking, how should I get started? Well, this is a 60,000 feet flyby, and we don't get into all the details of all the methodologies, but there are some simple steps that you can take to get started with grid architecture. First of all, most of the materials that we discussed today are available on PNNL's grid architecture website. Have a look. It has all the different industry structure diagrams, market structure diagrams, regulatory diagrams, and it also has much more. It has the reference architecture packages, which can serve as the starting point for utilities to think of the future architectures of the grid. And then there are other steps. So you can encourage utilities to apply grid architecture concepts to future-proof investments. And there are four steps that we thought of that you can take to get started with this. First of all, you can support a set of stakeholder workshops to move from those requirements to qualities to properties to the architectural elements, like I mentioned in one of the previous slides. I will just remind you that those qualities that we mentioned are the desired characteristics of the system from the user's point of view, while the properties are the characteristics of the system from the operator's point of view. And they help in determining the architectural elements that can help provide those properties to the system. So those can help in understanding what policy changes would be most effective. So determine the key architectural elements in this systematic manner. You can use the platform concept. So plan the core components and applications and make sure that the planning is done in such a way that future integrations would be easier and won't be lengthy, time intensive, or costly. And develop basic grid architecture diagrams to make visible relationships between the different stakeholders. There are already existing diagrams for different regional grids. They are available on the website, so you can definitely access them there. Next slide, please. And here we have come up with some questions that you can ask. So when proposing specific technology investments, has the utility gone through the process of identifying how proposed investments help achieve broader desired objectives, capabilities, and functionalities? So like grid architecture starts with the objectives, looks at the capabilities and functionalities to determine the technology investments. So that is a key concept that can be used to achieve this. Has the utility mapped key relationships and processes and determined how proposed changes will impact other industry actors and systems? What time horizon are you planning for, and how are you dealing with expected growth of DER to prepare your system for meeting decarbonization goals? If distributed architecture is a goal, has consideration been given to preparing for structural change from a centralized system? Should distribution operators' roles and responsibilities be changed? And if so, how does this impact grid control, markets, and oversights? We need to be cognizant of any implications from changes, and we need to plan for them. So these are very important questions. what steps are being taken to make integration of new applications into the system more cost effective and less time intensive. And we heard there are ways to do this. Next.
Seemita and
slide,
Ron, I want to go to questions now because we only have
Yes.
10 minutes left.
Yes.
We have some good questions. So let's start off with, and Ron, if you want to put your camera on and come up on screen too, thanks.
I'm here.
So do you have any advice on what software is useful for creating industry structure diagrams? You talked a little bit about this, I think, on slide 24, but can you say more about this for the benefit of utility regulators? So this is about software for creating these industry structure diagrams.
Yeah, actually, we use Visio to do these different sorts of diagrams that we use. There's some other software out there as well, but Visio is one of the more common ones, and it allows us to do the different types of diagrams that you've seen today.
Great, well, that's easy.
Yeah, yeah.
So, and you mentioned interacting with legacy utility systems on slide 25, one of your later slides. Interoperability is really tough. It's often a real issue with legacy utility systems. Do you have any advice for public utility commissions about, from the beginning and through the whole implementation, how to address interoperability issues with legacy systems?
Well, that interoperability with legacy systems is especially tough. Lisa, you're absolutely right about that. The thing to really pay attention to with interoperability is, of course, interfaces, and to ask the question of how is the integration of that interface going to be accomplished. It's actually an integration problem, and
Right.
it's how much time and how much cost is going to be associated with that integration. I don't have any silver bullets for the legacy systems. But in planning for the future, paying close attention to those interfaces and asking questions about how do you manage the complexity with the tools like we've talked about today can help, change that problem over time.
And this next question is mine. I'll just disclose, and this is friendly pushback just because this is what I feel commissions, including, putting myself in their shoes. I used to work at commission, might think, how much do commissions really need to understand about grid architecture when it's actually the utilities that will be implementing it?
Yeah, I agree fundamentally with that assertion. So the utilities need to know enough about it to have expectations to be shown work artifacts from the utilities that demonstrates that they're applying these ideas in their work. And hopefully some of the things we've shown today, help at least provide some base level information about the tools and techniques of grid architecture to help the commissions get started to be able to do that.
Seemita, do you have any additional comments on that question?
Yeah, I also essentially agree with what you said, but I think knowing the current system is incredibly important. And sometimes we know about sections of the system or certain attributes of the system which we deal daily with, but not the complete picture. So knowing the complete system using the grid architecture techniques, I think is an important step that can be taken, which will also help ensure that whatever proposals are being made are really beneficial and won't have any unintended consequences.
Great, thanks.
Yeah, Lisa, one quick comment on that. We interact with the stakeholders when we do these diagrams, especially the industry structure diagrams. And Seemita and I have had the experience of showing these diagrams to people associated with commissions as we're developing them in a particular region. And the response we'll get is, wow, we've never seen anything that gives us this kind of comprehensive view of the world we're living in.
Thanks. I think that was very helpful advice. So since the utility could be the distribution system operator, what kind of walls do you think need to be constructed with respect to the distribution operator to avoid conflict of interest? I know this is such an easy question, right? And what kinds of coordination will be needed between the DSO and the DO?
Seemita, do you want to take that one? Or do you want me to?
Yeah,
Nice hand up.
this is a challenging question. So I would say that, so first we need to think about the objectives we want to serve with having this DSO construct. And then
Right.
grid architecture will take up those objectives and obviously, like I said, the qualities and the properties, and then determine in a more formalized way than me trying to just say something as an answer, what the walls should be. One important thing that is that we should take away is the wall should be such and the interaction should be such that there should not be any conflicts. Like one entity class should not be sending the same signal to two different entity classes, and two different entity classes are making conflicting decisions and trying to control similar assets. So that should not be there. Tier bypassing should not be there. And it should be done in a more formalized manner than, so I'm sorry if I'm not really answering your question to the level of detail that you are looking for.
But let me add something to what Seemita said. So we talked about logical functional representations, and this is extremely important in the kind of question that you asked, Lisa, because we determine what functionality is required and what are the logical set of relationships associated with that functionality. Then we can step back and we talk about how are we going to implement that and look for the potential conflicts of interest and any firewalls that need to be built to avoid those conflict of interest and things once we've determined what the basic functionality is. And that, you know, it could be an operational functionality that has an economic construct, or it could be an economic construct that we're using for an operational functionality. But depending on the balance of those two, it'll probably drive us one way or another with respect to how we deal with the firewalls.
I think that those are helpful responses, and certainly commissions have experience with this that's somewhat analogous. There used to be very strong firewalls, say between transmission and resource planners, and then that didn't work out very well because you couldn't do coordination. So I think there's experience here also with restructuring. How about sort of related but different to one of the prior questions I asked? What can a public commission, a utility commission, do about grid architecture when a utility files a grid modernization plan if the plan hasn't addressed it, and most plans have not? So like the plan is filed, but the utility hasn't made the investment yet. I mean, normally a utility, makes an investment and then, they come in a rate case and it's, kind of late then. But there are a number of states are requiring grid modernization plans. A number of utilities are filing them on their own motion. So, okay, the commission gets the plan, says nothing about grid architecture. What should the commission do? What's your advice?
Well, I think that there was a little bit of experience like that in the New York Rev process. And if I remember correctly, they held workshops and they got experts involved who had the background to help guide the stakeholders in these workshops to begin to address these types of concerns. Of course, DOE has some of the regulatory support activities that make resources available. You're of course well familiar with that, but if you've kind of got to get a direction vector headed in the right direction and then let the momentum build, I think. Seemita?
I think another thing that commissions can do is ask about the rationale behind coming to that plan. Was there a formal approach taken which helps in predicting not just the small change, but the implications of the change? And further down the line in the future, will new changes be more difficult or will it be easier? So just ask those questions, even if grid architecture has not been explicitly named or has not been explicitly done. So that is something I would recommend.
I want to thank you both. I have to say, this is the best grid architecture presentation I have ever seen. I actually, it really clicked with me. I don't know if it's because it's like the 10th one, but I think it's the two of you really did a good job in making this quite understandable. And I think the urgency of actually doing this work is really evident. So thank you so much, Ron Melton, Seemita Powell from Pacific Northwest National Laboratory. And back to you, Danielle and Jessica, if there are any final comments here.
Thank you all for your excellent presentations, and we look forward to seeing our attendee audience next week at the same time. We'll put the last link for registration in the chat, and thank you again, Lisa and company. We'll see you soon.